values will apply. Okay. So again, keep this in mind that don't use a big NAND gate because the overall delay will be far worse actually. Going back to the inverters, we have found out that the best case is over here, but it gets inverted. So this is a slightly, this does not get inverted, but it is takes more area. This one is not bad. It takes less area, but the delay is 3 picoseconds more than this. So this type of dilemma the designer has to face. The designer draws a curve like this and finds out that if this is 1, this is 16, then how do I size the middle transistor, middle inverter? If I use 4, then it will be path F4 will be identical and will be minimum. So it will be here. But if I use 8, then the delay will be 13.3% more. Now, I really don't gain anything by making it 8. 8 if I make, because I have already area 16 here and 119. So why should I make 8? I would rather make A is equal to 2. Then I have the same delay, but the area is small. 1 plus 2 plus 16, 19, right? So you need to really make these type of calculations. Here, again, I will rather choose this one because in this case, my size will be 0.5, it will be smaller. So basically, you need to optimize this area of the gate versus the delay, and you need to draw a curve like this and find out accordingly. Okay. Okay. I will just try to finish as much as possible today about this, and then, as I mentioned, next class I will start adder circuitry. Have you started? Okay. Get started. So when is it due?
Next Friday.
This Friday?
Next Friday.
Next Friday. So I will start on Friday. Okay. So one of the problems, as we talked about earlier, that the internal node capacitances are ignored. So the delay is idealized, but in reality, because of the internal node capacitances, the delays gets, the delay is actually more than what you see. And there is something called body effect. What is the body effect? Who can say what is the body effect? Anybody? Do you know body effect? Yes.
It's when the VT or the threshold voltage changes because of the body to source voltage.
Because of that.
The body to source.
If the source is not grounded, right? If the source is not at the same voltage as the bulk,
Yeah.
then the threshold voltage will increase. Yeah. Correct? Yeah. We'll talk about that later more when we talk about the low power circuit design. But that's what it is actually. So that also we do not take into consideration. We are just considering all the threshold voltage is same, the delay is same. So in actual circuitry, the delay becomes if the threshold voltage is more, then the delay will be more, right? So these are the limitations of the logical effort. Chicken and egg problem. Need path to compute G. But the thing is that if I don't have the real design, how do I know what gates to use and how do I find out what the value of the G is? But don't know number of stages without G, okay? simplistic delay model neglects input rise side effects. There is no interconnect delay, and we try to maximize the speed, right? So we don't really try to look into the power consumptions and other issues. So we'll go into more complicated modeling techniques later. As I mentioned to you that these things are done at a different level. At this level, we are trying to basically select which topology to use for a decoder. We have seen that so many different things are there. If you try to bring in all these things, yes, you can do that, but it will take a long time. So there are 10 different options are there. So you'll be spending a lot of time doing detailed simulation, even though most of the cases are bad. Like, you can see that most of the options are bad. The real choice is this and this, okay, and this. So there are 3 real choices are there, and rest are bad. So why do you have to waste so much of time doing all those detailed level simulation? So that's why you calculate and converge on these 3, and then you can apply all those extra things to find out which is really the best one. So in a large chip design, we start with the behavioral model. The specifications are given, and then you write the Verilog code. You find out the system functions are met or not. So you provide the specifications of the system, and you verify that. And after that, from the Verilog, now if you're doing use the semi-custom design. In a semi-custom design, you give the Verilog code into your synthesis tool, and you press the button, and it gives you the layout, okay? A layout. This is not the best layout, a layout, right? Functionally correct layout. But if you want to make a full custom design, then you have to do all these things, architectural mapping, gate level design. You'll have to do the logical effort to find out which one to use. Then you have to optimize the speed, power, and noise optimization, gate structures and sizing, then transistor level circuit optimization through time simulation. So in this course, we are kind of ignoring this part. That would be 627. You'll be using a little bit for your control logic design and some of the register design, like instruction registers and address registers and all. But other things you'll be doing pretty much in details. The real difficulty is that since the project is pretty big, you are forced to pick up something without this. You know, you just, okay, I will do carry bypass standard. Why? Because somebody is doing something else, right? Say carry select adder, or somebody is doing ripple carry adder, somebody is doing carry lookup adder. So, but that's not the way the engineers choose, right? You'll have to find out, is there enough merit for a particular application? Carry lookup adder. Yes, carry lookup adder is faster generally, but is your design big enough to warrant a carry lookup adder? Can I use the carry skip adder, or can I use something else, right? So those type of decisions you'll have to make as a designer. Yes.
Are ripple carry adders used in industry at all?
Pardon?
Are people designing ripple carry adders for like current applications? Or do they?
I think all of you will be designing something else, right? Ripple carry adder is too slow for 16-bit.
Yeah, that's what I was saying. Like, do people
Still use that.
Yeah.
What do people use at all?
Yeah, in like companies and
In companies? Yes, yes.
yeah.
Yeah. I mean, a 4-bit chunk will show that carry bypass adder. First, we say a 16-bit adder will take a chunk of 4, 4, 4, 4, 4, and we'll use the bypass logic, but within this 4 is a ripple carry adder.
Okay.
If you go longer and longer, up to 8 feet, then maybe still, it's okay. But after 8 feet, the ripple carry adder is very slow actually.
the advantage of using it at all?
Advantage is that the other adders need some extra logic. Nothing comes free. Ripple carry adder, you are just connecting the C out of the next stage, previous stage to the next stage C in, right? So just one line. But in other cases, you need some extra logic, extra thing.
Okay.
We'll talk about that actually. So my point is that we need to really figure out that what should be your right choice so that you get the lowest power consumption or you get the high speed, so those kind of things. So this is a tool I was talking about in Bell Labs. They used to have, when I used to work in Bell Labs there, we used some of it actually. It simultaneously solves the sizes of the different transistors, and then it tries to find out that what will be the optimal value of the different gates. I will run a manual example just to show how it works, but it is difficult for larger circuits, so that's why this tool, TILOS, time logic synthesizer, they developed at the time, and people use some version of that. Now, I don't have time to run through this one. This is an example